Welcome to a talk on dynamical downscaling. I'm Cindy Bruhier. In this talk, I will focus on an overview of downscaling and best practices with a focus on extreme weather over climate timescales. To set the stage, let's first look at the difference between weather and climate. Climate is the average weather over a very long time period, typically 30 years, while weather is what is happening right now. When we want to look at extremes and how climate change will impact them, we are interested in weather over long timescales. If we look at the weather climate from a time perspective, weather predictions are typically out to a week. Climate projections are typically done for decades to centuries. Climate predictions are typically subseasonal to decadal. And this is also the time period we typically use when looking at extreme weather changes. Weather models are dependent on getting the initial conditions correct, while climate predictions are dependent on external forcing like CO2 changes in the future. When we focus on subseasonal to decadal, both of these are important. In the next couple of slides, we are going to look a bit deeper into the difference between global and regional models, as well as the options available for downscaling. Global models, by definition, are run over the entire globe, and therefore no boundary conditions are needed for these models. These models typically have an atmosphere, land, and ocean component, and these components are typically fully coupled. The models need initial conditions and are run forward in time. They do require hundreds of years of spin-up, though, before they can be run forward in time. Regional models, as the name suggests, is run over a really small part of the globe, so boundary conditions are needed to bring in the weather into the domain of interest. These models typically only have an atmosphere and land component, and these components are typically coupled. These models also depend on initial conditions, but because they are on a limited area, we also need boundary conditions. And as you might have noticed, we do not have a fully coupled ocean, so we also need boundary conditions for the ocean. The advantage of these models are that they do not require very long spin-up time periods, typically weeks to months, because they take advantage of the spin-up that was done in the global climate models. Downscaling options. There are a lot of models available to downscale. The two that I want to present here today would be WRF and MPAS, and these are models that are developed and supported by NCAR. They are both good models and good choices for downscaling. WRF is a more traditional model using nested options to zoom into the area of interest. MPAS can be run both as a global model or a regional model, and it uses mesh refinement to zoom into the area of interest. I do want to highlight the COAWST modeling system as well. COAWST is a modeling system that uses WRF as its atmospheric component. This model also has a fully coupled ocean model, a wave model, and a sediment transport model. This model is developed by USGS, and the main developer for this model is John Warner. In the next couple of slides, we are going to look at the strengths of different modeling approaches and when to consider downscaling. So we have talked about GCMs and RCMs. GCMs provide the basis for understanding and predicting climate variability and change. They do require long spin-up periods, and they typically have very low resolution. They are not that expensive to run, therefore they are typically run over very long periods of time, out to centuries, and a lot of them also have ensembles, making it a very rich data source. Regional climate models provide information both locally and on extremes. They are typically nested within reanalysis or GCMs. And as I said before, they require boundary conditions. They are pretty expensive to run, and therefore most people can only afford to run them over short periods of time and run limited ensemble members. Advantages are that they are high resolution and they do take advantage of the spin up that come from the GCMs. I do want to mention statistical downscaling because this is a great way to bridge the gap between global climate models and regional climate models. They're inexpensive to run, they're easy to run, you can run them for really long periods, and you can also experiment with different methods of statistical downscaling. I'm not going to go into detail into statistical downscaling in this talk because there are a number of other talks in this series that talks about statistical downscaling. So what are the questions that you need to ask before you even consider if downscaling is correct for you? Here's a couple of questions that I suggest you consider. What is the science questions that you want to ask? Can a global model answer the science questions, or do you need to downscale to answer your questions? What is your topic of interest? For instance, cyclones, precipitation, snow. And also sub-interest. For instance, if you're interested in genesis of tropical storms, you might not need a regional model. But if you're interested in the intensity of tropical storms, you probably will need a regional downscaling model. You need to consider how big the area is that you're interested in. What's the period that you're interested in? But do not forget about things like the input data, problems with the input data, the quality of the input data, how much resources do you have to run your downscaling experiment, and what are you going to do with the data after you have generated it? So from the modeling perspective, some of the things you need to consider would be the model resolution, the domain configuration, model physics, and input. And I'm going to go through each of these in a little bit more detail in the coming slides. So first of all, I am going to look at model resolution and domain size. And to set the stage, I'm going to give you a couple of examples. This first example is winter precipitation. So at the top, I'm showing you observations for a 30-year winter precipitation average. And you can see that on the coast, we have more rain than in the center of the country, and we have a lot of detailed information of precipitation around the mountains on the western side. On the bottom, I'm showing you on the left-hand side a model that was run with low resolution, and on the right-hand side, a model that was run with high resolution. And you can see in the low resolution model run, you do have the drier areas in the middle of the country and wetter areas on the coasts. If you're just interested in these general precipitation patterns, a low resolution global climate model will be sufficient to answer your questions. If you are interested in extreme precipitation and detailed impact of orography, that is not going to answer your science question, and you would probably have to consider downscaling to give you the orography effects that you would see in a high resolution model. If we look at the impact of snow, the two figures that I'm showing you is from a global climate model on the left and a regional climate model on the right. And you can see that the global climate model does not give a realistic snowpack, and it's therefore not useful for studying the extent of snowpack, runoff, or future changes. So if snow is what you're interested in, you're going to have to downscale with a regional model to get the right representation of snow in the model. And the last one I want to show you is a hurricane example. If you're interested in tropical storm tracks and frequency, you can probably get away with a low resolution model because GCMs does a fair job of getting tracks and genesis correct. If you're interested in the structure of models, you could probably get away with about a 36-kilometer model, as I'm showing you here in the upper right-hand side. If you're interested in rain bands, you can see they're missing in the 36-kilometer model, and you probably have to go down to at least 12-kilometer model to get the rain bands correct. If you're interested in intensity, you're going to have to go much lower. You can see I'm showing you here a 36-kilometer model that is truncating at category 2 storms, and a 12-kilometer model that is truncating at about 12. And to get higher category storms, you would have to go down significantly lower. Now, let's look at how much it might cost to increase the resolution. Here I'm showing you a picture with a complex terrain. If we do a 20-kilometer model, we might have, in this case, 20 by 15 grid points in either direction. And we say we need to do 30 time steps for a 1-hour simulation. That would give us approximately 9,000 operations to complete 1 hour of simulation. Let's look what happens if we halve the resolution. In this experiment, we are going to assume that the vertical resolution stays the same, although we're going to look at this in a little bit more detail later on, and you would see that is not something you would typically do. If we halve the resolution, we double the X and Y components, and we also double the time requirement. So now we're up to 72,000 operations for a single year. If we double the resolution again, we're now at 5 kilometers, and we over half 1 million operations for a single hour of simulations. And here I'm showing you 2 kilometers, and we're now at 9 million operations. So in summary, to go from a 20-kilometer resolution model to a 2-kilometer resolution model, we increase the computer requirements by at least a factor of 1,000. In this slide, I just want to summarize some of the impacts of resolution. I'm showing you a couple of images of what terrain would look like going from 250 kilometer to 10 kilometer. You can see at 250 kilometer, you can see continents, but they're very smooth. At 100 kilometer, the mountain starts appearing more realistic, and we can start seeing some of the bigger lakes. Whereas when we get down to 10 kilometers, it looks very realistic. If you're only interested in general circulation, you can probably get away with a resolution of about 200 kilometers. If you're interested in continental scale flows or carbon cycles, you probably want to be below 200 kilometers. If you want to look at MJOs in convection, you probably want to be around 100 kilometers. And when you start looking at hurricanes, you need to be at 50 to maybe tens of kilometers. And no talk will be complete if we do not also talk about vertical resolution. If you increase the horizontal resolution, you should typically also increase the vertical resolution. We typically want to see more layers in the boundary layer than in the top, but do not neglect the top and make the levels too wide in the upper atmosphere. We also recommend that the model top should be at least 50 hectopascal or higher if you can afford it. I'm now going to switch over to look at domain size and placement. In this example, we're looking at the influence of lateral boundaries. And I'm showing you two figures. They both plotted on the same domain, but the one on the left-hand side was simulated on a large domain, while the one on the right-hand side was simulated on a small domain. And you're looking at the 12-hour simulations of a 250 hectopascal winds. You can see on the one on the left that was simulated on a large domain that the trough is very well developed. The one on the right has a very wide trough. And although I'm not showing this to you, the one on the right-hand side looks very similar to the era, Here we are going to look at an example of the influence of the lateral boundaries. What I'm showing you here is two figures, both of them plotted on the same domain, while the one on the left was simulated on a very large domain, and the one on the right was simulated on a small domain. And you're looking at the 250 hectopascal winds. You can see the one on the left that was simulated on a large domain as a very well developed trough, while the one on the right-hand side has a wide trough structure. Although I'm not showing you this, the one on the right looks very similar to the driving data. And in this case, nothing was gained by running a downscale experiment on a very small domain. Other considerations to be aware of is where the high topography is. So avoid placing your domain over a very high topography. You also need to consider what the driving data does well and what its shortcomings are. You need to consider the resolution of your driving data, the area that you're interested in, and what is upstream. So as an example, what I can share with you here is if you want to simulate tropical storms over North Atlantic and your driving data do not get the easterly waves correctly, you are potentially not going to get the correct genesis for your tropical storms, in which case you would have to increase your domain and move it further out to the east so that your downscaling simulations simulate the easterly waves correct, and therefore it will enhance the simulation of tropical storms. I'm now going to switch over looking at model physics. So some of the considerations when you do dynamical downscaling is which physical package to use, but also how well does your physical packages work together. Physical packages have important differences. For instance, some microphysics has snow while others do not. And if you're not interested in snow, that might not be important for your simulation. Some PBL schemes do their mixing different. Some cumulus schemes have a shallow convection scheme, and some do not. You also need to make sure that the physics that you're using has been tested for your area of interest, and also consider how expensive they are to run. I want to leave you with this thought. Remember, you're not doing model development. This is about a scheme that's going to help you answer your science questions. So pick something that has been tested. In this example, I want to show you a 24-member WRF ensemble that was run with different physics over the domain that I'm showing you on the left. So the 24 ensemble members were made up with 2 different radiation schemes, 2 different PBL schemes, 3 different cumulus schemes, and 2 different microphysics schemes. In this example, I'm showing you the daily average maximum temperature for the entire North America and the entire South America. The black line is the observations. The blue line represents 12 of the simulations run with 1 radiation scheme. The pink line represents the other 12 run with the other radiation scheme. And you can see that if you're over North America, it doesn't really matter which radiation scheme you pick because they both do very well in this area. If you were in the southern over South America, that really makes a difference which radiation scheme you pick, because the CAM radiation scheme does very poorly here, whereas the RRTMG scheme did very well. If we look at tropical storm genesis, the picture is even more varied. At the top, I'm showing you in the gray bar the average number of tropical storms the North Atlantic experienced per year. And in the upright bars, I'm showing you the genesis for each of these simulations. And you can see they are spreading from about 2 or 3 a year to over 25 storms a year. If we combine them by the different physics, you can see that radiation and microphysics makes very little difference in the choices, but cumulus and PBL has a very big impact on the genesis of tropical storms. And this is even more profound when we are combining different schemes. So if we combine a scheme, a cumulus scheme and a PBL scheme that both over-predicted the number of storms, you can see that we significantly over-predict the number of storms. Whereas if we combine this same scheme with a PBL scheme that predicted lower numbers of tropical storms, we get correct numbers of tropical storms. So the combination of the cumulus and PBL scheme in this case made a very big impact. Now we're going to look at input data. And remember, we need initial conditions, we need boundary conditions, and we need lower boundaries for our regional downscaling. And I'm specifically going to look at regional climate models and downscaling from there. Remember, I said in the beginning, our regional climate models typically are run over very long periods of time, and they also typically have ensemble members. So you could have a number of ensemble members to pick from to drive your RCM. On the right-hand side, I'm showing you a 55-year temperature trend from a 40-member ensemble. The top is the average for the 40-member ensemble. The middle is the warmest ensemble, and the bottom is the coldest ensemble. So which one of those should you pick if you want to downscale? If you can afford an ensemble, I would suggest pick a high one, a medium one, and a low one, which would give you the entire spread for the future. If you can't pick that, I would suggest either pick a middle of the road or a high one, which would give you the most extreme conditions that you could expect in the future. A question that we often get is, should I just average those? And the answer is no. If you average it, you're going to smooth out the extremes that you are interested in. So rather pick one of those and interpret your results on the basis of which one you picked, rather than using an average. I'm now going to switch over to looking at biases in climate models. Most of our climate models do have biases in the absolute fields. The figure I'm showing you here is the August, September, October average sea surface temperature, and it is a difference between a climate model and observations. And you can see that the climate model is too cold over the Atlantic Ocean. And if we look at the absolute fields, this is a time series of the black line shows you the SST for the observations, and the blue line shows you the SST from the climate model. And you can see they are out by more than a degree between the two of them. So the absolute fields definitely problematic. And specifically for tropical storms do not form when the SST is low. So you would want to bias correct those to simulate tropical storms correctly. But if we look at the anomalies in this field, you can see that these two lines collapse on top of each other, and the climate model does do the anomalies very well, although the absolute fields might not be as well represented. The impact of that specifically for tropical storm is shown in this picture. At the top, I'm showing you tropical storms from the observations. And on the bottom, on the left-hand side, I'm showing you a regional climate simulation where we did not bias correct, and on the right where we did bias correct. You can see the very big impact it has on tropical storm genesis. So how do you bias correct to prevent this type of problem? I'm showing you here a cartoon of a quantity over time. So we have a quantity that is represented over time. And what we can do is collapse this quantity over time into a probability density function distribution or a cumulative distribution function, so a PDF or a CDF. And we can use this PDF and the CDF to build our bias correction methods on. Here I'm showing you 4 bias correction methods that is typically used. The top one and the one that I would actually recommend you would start off with would be altering just the mean state. So what I'm showing you here is a PDF. The one in gray is, say, for instance, from the climate model, and the one that is dotted might be from your observations. And you can see there is a mean difference between the two, and you can use this mean difference to adjust your climate model. A slightly more complicated method is showing on the left bottom, where you can use both the mean and the variance from the PDF to correct your biases in the model. It is a more complicated method, and you don't always benefit from doing both of those. Another popular method is shown on the upper right, which is using a quantile mapping. In this case, we use the CDF, and we map the one CDF to the other CDF, and thereby adjusting the bias in the model. And the last one is looking at a change factor. This is typically used if your distribution is more Y-ball. And in this case, we would use both the scale parameter, which gives you how high this peak is, and the shape, how wide your PDF is, to bias correct. I do want to mention a bias correction method called pseudo global warming, or PGW. PGW is very similar to changing the mean state, although there are very small differences between them, which makes the one more powerful for certain conditions, whereas you might want to consider PGW for a different approach. And in the next slide, I'm going to explain the difference between these two. If we go back looking at our sea surface temperature and our sea surface temperature observations and the global climate model that is different by about a degree. In the PGW method, we would pick a current climate and a future time that we're interested in. Say we're interested in the 2050s, we might pick a time period around the 2080s, find the delta between these two time periods, and add the delta back to the current climate, which will then give us this green representation in the future. Alternatively, we could have picked maybe a time in the 2000s, do the same, get the delta between them, apply it to the current time period of the 2000s, and we would get this representation of the red one in the future. And you can see that although they are very similar, there are differences in the variability of these two time periods. In the mean state bias correction method, we would use the mean of the current climate and then get a delta and add that back on to the current climate in this case. And this means that we are using the variability and the trends from the climate model So the variability and the trend comes from this blue line. We get the mean from the observations, which is the black line, and we add that mean back onto the climate variability, which would then bump us up to this red line. So in effect, we're only lifting up the climate trend by a specific delta. The PGW method is therefore highly dependent on the period that you pick, which makes it very good for event attributions. So for instance, if you want to see what Hurricane Katrina, which happened in 2005, would look like in the future, PGW method is a great way of seeing how that storm will change under climate conditions. If you want to look at extremes over a long time period and more generally how all extremes is going to change in the future, I would recommend you use the mean state bias correction method. And with that, I want to say thank you for listening. And I do want to remind you of the questions that I posed before you even consider bias correction, or before you even consider downscaling to a regional climate model. So what's your science questions, as well as your input data and your computer resources. And if you do decide to do dynamical downscaling, remember the things that I mentioned to consider: your model resolution, your domain configuration and placement, model physics, as well as the input data. And on the input data, remember, absolute fields from climate models often have biases, and consider how you bias correct them carefully before you move forward. Thank you for listening. And if you have questions, I welcome you to send me an email.